An important thing that we need to know as metallurgists, um, material scientists, material engineers, welders, machinists, CAD technicians, is how do materials break? The common types of fracture are ductile and brittle fracture. Ductile fracture is preferred in most applications. Ductile fracture is a type of fracture characterized by extensive deformation of plastic or necking. This usually occurs prior to the actual fracture. The term ductile rupture refers to the failure of a highly ductile materials. In such cases, materials pull apart instead of cracking. In ductile fracture, there is absorption of massive amounts of energy and slow propagation before the fracture actually occurs. By understanding ductile fractures, engineers are able to develop more dependable and safer industrial products and materials. A fracture is one of the most crucial concepts in terms of materials engineering. In general, fracture is referred to as one body going through separation due to imposed stresses. Almost all engineering materials undergo only two types of fracture modes, ductile and brittle fractures. Ductile materials exhibit massive amounts of plastic buckling or deformation in comparison to brittle materials. In ductile fracture, the crack grows at a slow pace and is accompanied by a great deal of plastic deformation. In this case, the crack does not expand except when high levels of stress are present. Under the view of a microscope, the surfaces of materials with ductile fractures appear irregular and rough and exhibit some dimpling. But in almost all design situations, materials that exhibit ductile fracture are preferred for various reasons, including ductile materials deform plastically, slowing the fracture process and allowing more time to correct the problems before failure. Higher amounts of energy strain are required to deform a ductile material. Ductile materials are forgiving, and any error in the design process does not result in catastrophic failure. That is why ductile fracture is preferred over brittle fracture. A brittle fracture is the breakage or cracking of a material into discernible parts, from which no deformation can be identified, basically a clean break. It is characterized by a rapid crack propagation with low energy release and without significant plastic deformation. The fracture may have a bright granular appearance. The fractures are generally of the flat type, and chevron patterns may be present. In brittle crystalline materials, fractures can occur by cleavage as a result of a tensile stress acting normal to crystallographic planes with low bonding, in other words, cleavage planes. In amorphous solids, by contrast, the lack of crystalline structure results in conchoidal fracture, which cracks proceeding normal to the applied tension. In a brittle fracture, cracks run close to the perpendicular to the applied stress. This perpendicular fracture leaves a relatively flat surface at the break. Besides having nearly flat fracture surface, brittle materials usually contain a pattern on their fracture surfaces. Some brittle materials have lines and ridges beginning at the origin of the crack and spread out across the cracked surface. Since there is very little plastic deformation before failure occurs, in most cases this is the worst type of fracture because the visible damage cannot be repaired in a part or a structure before it breaks. Brittle fractures display either transgranular or intergranular fracture. This depends upon whether the grain boundaries are stronger or weaker than the grains. Let's talk a little bit about transgranular and intergranular fracture. Transgranular fracture. The fracture travels through the grain of the material. Cracks choose the path of least resistance. Intergranular fracture. The crack travels along the grain boundaries and not through the actual grains. This usually occurs when the phase is in grain boundary is weak and brittle. Remember from chapter 4 that stress is the force applied to the material, such as tension, compression, shear, flexure, and torsion. Strain equals the deformation divided by the original length. On the stress-strain diagram, we can see the plastic deformation differences in ductile and brittle materials. With ductile materials, the extensive plastic deformation and the ability of a material to absorb energy before failure is also called the toughness of the material. In the second example, the shape of the fracture can give a clue to how brittle or ductile a material. Here are some examples of ductile fracture process. The first example shows the fracture process in a ductile material. A. Material experiences necking. B. Small microvoids start to develop. C. The microvoids combine to form a crack at 90 degrees. D. 45-degree angles form as the material reaches its maximum shear stress. And then E. We have complete failure and fracture of the material. The second slide shows the cup and cone fracture in the aluminum. Fractographic photos show the voids in tensile failure versus shear failure. Brittle fracture. Notice the clean break without much deformation or cup and cone fracture. Very little or no sign of plastic deformation. The breaks are quick. They're clean breaks, usually at a 90-degree angle, and breaks along the cleavage planes. As a metal is cooled, it decreases the ductility and becomes more brittle. Determining the temperature for what a material starts to change to being brittle is known as the ductile to brittle transition temperature. Ductile to brittle transition. Low temperatures will embrittle steels. The first all-welded Liberty ships produced during World War II failed by catastrophic fracture when exposed to the cold North Atlantic sea temperatures. Fatigue cracks formed at the corners of the square hatches and spread rapidly by brittle fracture. Most famous ship, think about the Titanic. Fatigue is a material's failure under fluctuating and/or recurring stresses. Fatigue failure can occur much lower than the material's tensile or yield strength under a static load because of the repeating loading and unloading of the applied stress, estimated to cause 90% of all metallic failures. Factors that affect the fatigue life: the magnitude, how heavy is the stress, the mean, the amplitude, the quality of the surface. Is there scratches? Is there a sharp transition? So how do we solve those issues? Well, we can polish it, which removes the machining flaws. We can introduce compressive stresses, compensate for the applied tensile stresses into a thin layer by shot peening. That's firing small shot onto the surface to be treated. High-tech solutions are ion implantation, laser peening, where they're actually changing the flatness of the part by introducing valleys, and so it's not just straight where a crack can occur. Case hardening, so they can put carbon or nitrogen-rich outer layer in steels by atomic diffusion from the surface. It makes a harder outer layer and introduces compressive stresses. Now the thing is, with case hardening, it's usually done on low carbon steels and anywhere from 5 to 15 thousandths deep, which leaves the inner material malleable. Again, it gives it a hard surface. Optimizing the geometry, avoid internal corners, notches, by putting fillets and chamfers, so you don't have sharp 90-degree corners which tend to break, which is the weakest part of a part. Factors that affect fatigue life: environmental effects, thermal fatigue, thermal cycling causing expansion and contraction, heat and cold. Solution: eliminate the restraint by design. Use materials with low thermal expansion coefficients. Corrosion fatigue, chemical reactions, rust, so on and so forth, introduces pits which can act as stress raisers. Corrosion also enhances crack propagation. How do we solve that? Well, we decrease the corrosiveness of the medium if possible, if you can use a different material, or we can add a protective coating, add residual compressive stresses.